Hello, everybody. I see that it's a really packed room this morning. Thank you for being here on a 9 a.m. session. I know it's a bit early in the day, but thank you for attending. And today we're going to talk about the technical journey of Expedition 33, how we started from a prototype and all the challenges that we encountered on the way to shipping the game. So bonjour mes amis. Who am I? I am Tom Guillermin, one of the co-founders of Sandfall Interactive. And on Expedition 33, I've been technical director and lead programmer. My background before Sandfall was gameplay programming in the Ubisoft group, both in Montpellier and Massive Entertainment in Malmö. So it's good to be back here in Sweden. The agenda for today, we're going to talk about how we built the core game, the core gameplay loop, and all the challenges that came with fixing the game as we went with a pretty small team. And then the last point on which we will spend some time are all the challenges with shipping the game. Because having a cool gameplay loop as a prototype is pretty easy, in particular with Unreal, but shipping the game, it's another dimension of problems. A quick disclaimer. Expedition 33 was the first project of Sandfall, so keep that in mind. And it was also the first project for us on Unreal that we were shipping in a professional capacity. Not everything you will see today are best practices or approved by Epic, basically. And of course, we did work on some other games before in other companies for a few members of the team. But it's very different when you are part of the big company like Ubisoft compared to creating a more independent studio with a smaller team where you have to do more yourself. So please be kind to the ugly stuff you will see today. So first of all, some of you might know, but there is a big elephant in the room. Here it is. Hard to miss it. And wait, it's a blue elephant? Oh no, it's a blueprint elephant. That's right. 95% of the core gameplay logic of Clair Obscur Expedition 33 is implemented using blueprints. I know, that's a lot, right? We do some C++, though. We do have some of it. The main reason is to expose even more stuff to blueprints because we love them. There were some measured performance bottleneck on the project that we did convert some of the blueprints into C++ when we were having issues. It was mostly when iterating over a large number of elements where basically the overhead of the blueprint VM is too costly. And of course, there are some new and more experimental features in the engine that sometimes don't have a blueprint API yet for us to use, like the math system, for example. So our engine programmers are basically did a whole bunch of C++ to support the crowds in Lumiere. So that's the three main points where we would be using C++ instead of our beloved blueprints. So I know you are not gonna let me get away with that this easily. So I have to explain a bit why we do have that many blueprints in the project. And it boils down a lot to the history of the project and how it started. In the very beginning, it was a personal project from Guillaume Broche, our creative director, and I was helping him from time to time. So here you will see the evolution of the team size versus the programmer headcount at Sandfall. So at the very beginning, Guillaume doing a lot of things and me helping from time to time. So let's count 0.5 as my contribution there. And at that point already, it was super important to not prevent him, because Guillaume doesn't have a programming background. So it was important to not stonewall him out of making contributions on the project by me writing some C++ code. So I would adapt to his way of working with blueprints. And the team started to grow. So we did a first prototype, still me alone on the programming side. And then we did a fundraising. So for that, we also did specific prototypes. The team started to grow. We had the core creative team with Jennifer, our writer, Nicolas, our art director, and Lorien, the composer. Francois, our CEO, had also joined at the time. But I was still sole programmer. Then the vertical slice. So we had a bigger team. We were creating more content, and yet, after the vertical slice, we signed with Clair Interactive as our publisher. They financed the whole project. The team grew bigger as we were moving towards alpha, and we kind of learned from the mistakes of the past. So the programming team grew a little bit bigger, but still not crazy. And as we were nearing the end of the production, we recruited a UI programmer. What a luxury! One more guy. And finally, the closing part. The team grew substantially bigger. But yeah, it was still the four of us, but we did have some external help from our publisher Kepler and Ebb Software as programming backup, which was very useful. So, but yeah, the history is very important to understand how we were working together, and I'm gonna dive a little bit more into that, like the synergy between programming and content creation, because it's an RPG. We do have a lot of content in the game. So I will explain a little bit more how we work. But first, so as I said, like very limited programming bandwidth. So that meant we had to focus on what was important. A bit cliche, but basically not reinventing the wheel. Working with Unreal, you have a lot of stuff that comes for free. The first one is engine updates. I've said it before, but yeah, we love getting new versions. You have so many new features, bug fixes, performance optimization. It's amazing. It all comes for free. And anybody that ever did an integration of the code, a new major version knows why it's air quotes free. But yeah, we love updates. Unreal 5.4 released in April 2024, and we had our first master version basically ready in September 2024. So we did a major update, yeah, like less than 5 months before having to ship the game. Yeah, we were confident or reckless, I'm not sure which, but yeah. So also we really follow Unreal's paradigm. Yeah, if you're trying to, as a small studio, to fight the way Unreal is proposing to do things, it's a losing battle, because as I said, resolving on the next version of the engine will be really painful, and you will have to redo a lot of the work you did previously. And when you do follow Unreal's paradigms, you do have a lot of editing power for free. You don't have to create too many tools, too many custom tools to edit your data and do stuff in the engine. And in the end, we ended up having really few custom tools in the engine. Most of the data setups for Expedition 33 are very vanilla in the way they are set up. Speaking of vanilla, yeah, we use all the tools that are available. We used the sequencer a lot in battle. We treat all the small gameplay segments in battle as small cinematics. So basically, it gives a lot of creative freedom to the content creation team to put as much polish as you want without requiring a programmer to trigger VFX, SFX, and animation. So we really push that to what we believe was the limit. But yeah, same for UI, all the gameplay systems, we really try to use what's there to focus on gameplay and gameplay content instead of trying to do some crazy technical innovation, which can be good, but our point was more to innovate on the gameplay rather than the tech. We do experiment a lot and adopt some of external plugins, because basically when you have a problem in Unreal, well, sometimes, a lot of times, it happens that other people had the same problem, and some of them did package that as a plugin, sometimes for free, that you can find on GitHub, and sometimes you can find them on the marketplace. So we did spend a lot of time iterating on some plugins. Sometimes it was like a good starting point that we completely replaced later in the project, or some of the plugins we just kept. For example, we have an amazing plugin that allows us to do Niagara particles in UI elements, which is great when you are in the polish phase of the project. And like to illustrate the mindset of not reinventing the wheel, we also apply that to non-technical stuff, like megascans. We love megascans. We've been using them since they were available in the engine. We also do spend a lot of time customizing them to make sure they match the artistic direction of the game. But yeah, it's great to have a starting point for level art in a level, and some of them we just use as is, like some foliage element, which are pretty standard. So going back to blueprints, there are a few other benefits rather than basically team structure. It's a curated subset of the engine API because basically not everything is exposed by default. And when you're working with an engine you don't really know because it was like a first project, it's really important to reduce the amount of noise when you are trying to comb through the API to build your feature. So having this subset really helps focus on the right way of doing things. Might sound a little bit stupid maybe, but the autocomplete, it is so good. Like compared to some of the C++ autocompletes, it's really powerful, really reactive, and it actually autocompletes when from both the target but also the parameters. We need that for C++. Stability. When you are trying to access a non-object from your gameplay logic, for example, well, in C++ that would be just a crash. Unreal has a way of providing default behavior by not executing function and default constructing the function outputs. So show can go on in a way. So you will have weird issues, but you won't have a crash, which is, once again, important when you're iterating on gameplay and programming time is a scarce resource. Yes, it has been shared yesterday in the 101 tips and tricks for Unreal. We've been using it a lot at Sandfall. Please enable this to catch logic errors in your gameplay, in your blueprints. And there are some challenges. Of course, it facilitates some bad memory practices. Everybody's aware, I think, of the cast nodes loading the type. You can also have orphan nodes, for example, member function calls in your blueprints. And when you are leaving that in your blueprints, well, the type associated with that will be still a dependency of your assets. There are no merging tools that we knew of, so if there is one, please scream right now, which can be complicated on some core files in the project where you can have some congestion due to blocking with perforce. And it's also harder to debug or iterate in package build compared to C++. In C++, you can just recompile locally and hot swap the exe, and that's it. With blueprints, it's more complicated to do that, so that's one thing to keep in mind. What about performance? A wise person has said that another wise person said, use a profiler, so I'm gonna just stick to that. So another point with limited programming bandwidth is that you have to focus on content horizontality, and by that I mean focusing on a restricted number of features, but create as much content as you can with those features. And to do that, you have to give autonomy to your game designers. And maybe one important point to mention is that all the game designers at Sandfall are technical game designers. So they not only do amazing Excel spreadsheets, but they also go in the engine and they create the content. So programmers don't have to. Hey. The way we work, programmers create building blocks for game designers. I mean, it's pretty standard stuff. So gameplay programmers would work on the core layer of the gameplay system. We would have then a surface layer, which is like basically a scripting API for the designers to use. We have different ways of doing that we'll detail quickly. And then from that, game designers create all the game content, and hopefully there is as much as humanly possible. So we'll focus quickly on the scripting API part, which is important because that's how you actually empower your game designers, because the quality of the content they can and the variety of the content they can do with your system depends on the quality of the scripting API. So we have two ways of creating content. The first one is imperative, and in Unreal that mostly means blueprints. So an example is our battle buff, battle buffs are basically a piece of logic that we attach to a character for a given number of turns, because we are turn-based. So the most obvious examples are status effects, like burn and stun. But we also use this system for all the passive effects that you can find in the weapons, in the lumina that your characters can learn. So it's a very powerful system that allows you to react to what is happening during battle. We also use that for some heroes' unique mechanic, usually to modify the damages, that kind of things. We also have some more bespoke battle buffs that are used to implement some enemies' unique behavior. So we have the Brazzler, for example, who is switching between fire and ice stances with different elemental affinities. And yeah, some of you might know it, the mime, which is, yeah, I won't spoil the mechanic of the mime, but yeah, sorry for that one. And also, of course, for internal things, you can have markers and cooldowns. It's basically a free, like, game designers are really free to use the system as they wish. So how do we create a battle buff for Expedition Series 3? So we have a base class BP battle buff instance, blueprint, of course. So we create a child blueprint from that, and there will be two parts of the setup. The first one is overriding a few class defaults. So of course you have the default turn duration at the top, and then you have some like gameplay aspect with character stat multiplier that you can apply on the character. Then some display information that we show in some of the UI panels. And then we have different settings to control the stacking method, which is also important thing to handle for buffs. And then the core of the buff will be implemented by overriding functions and events. So like this is just like part of what is available for designers to override. You have ways of overriding damages at different stage of the damage calculation process. We will see like a quick example of that, but you can virtually change like almost everything in the battle system. You can change when an action point is gained, for example. You can modify that. You can change heal. You can prevent death. Like there is so many things that you can do with the system. So here is the marked buff. So the marked buff increases damage, the next damage received by a character. So the function we override here is process received final damage. We do some filtering because we don't want this effect to trigger on some passive effects. Basically, we do some user feedback, we do some damage modifiers, and then we just mark the buff to be removed. So pretty straightforward. And yeah, the whole game is made like that. So we also do declarative. For this, we have a system called game actions. A game action is basically an asset that can trigger gameplay features of the game. It can be battles, it can be cinematic. So you don't have to do blueprint scripting as a designer to use the system. You only choose the type of action you want to trigger, and then you will have, of course, all the parameters. So which battle to play, or which cinematic, or which dialogue to start. And you can, of course, compose multiple game actions in the sequence. So this is on the right, like a real-world example that we have in the game. I mean, it's a bit small maybe, but basically we have a cinematic, and we are excluding characters from the party, healing, starting a battle, and then based on the outcome of the battle, we do different things. So those two systems are really powerful, and as soon as the programmers are done creating the building blocks for the designers, it's from that point on, it's mostly maintenance, and programmers are not involved in like the breadth of content that we have. So it's great to give autonomy to create content, but part of this autonomy is also about fixing issues in content, because of course there are going to be some problems, and you want the game designers to have autonomy in finding problems and solving them without your help. So the first layer we have is in-editor validation when you're working on the asset. We have, of course, the static asset validators. We use the default, the vanilla system from Unreal. So a lot of that is also implemented in blueprints, because we only have access to the blueprint namespace from blueprints. We also have specific helpers to help us validate actor classes. The idea is that we spawn an instance of the actors, so we have a more convenient access to component hierarchies, mostly because it can be a bit more difficult to explore that in the raw data source of the actor class. And last but not least, we also have validation on each individual placed actor. So we created an interface that you can use on both actors and actor components, and it will run on every single instance present in the level and do the logic. So it can be used for many things, like checking for occlusion or checking for collisions and that kind of things that can be really painful to manually check for level designers when you have like pretty big levels with a lot of scripted content. But it's not always possible to detect everything statically. Sometimes you just make hypotheses as a programmer, and when your code is executing, it's not, the hypothesis is not correct. So it's important to feedback that as well, that things are going wrong. And to do that, I will give you a brief history of how we feedback logic errors at Sandfall. So first, an error message in a bottle. We were outputting errors to the logs. So it's amazing when you put an error starting with error. It's in red in the logs, pretty obvious. But well, you do have to look at the logs to notice that, and sometimes people don't have time to do that. So we thought, okay, we need to have the error coming to the user, something more obvious. So we started putting stuff on screen. Great, very visible. You don't have to leave your play in editor session to see it. But that's how it turns into quickly. And this very new error that is actually related to the new content you're working on, well, you're probably missing this. So from this point, what more could we do than showing stuff over the gameplay? Well, completely interrupting the gameplay, right? So showing a pop-up from the gameplay thread, interrupting the gameplay was for us the best way to provide feedback on important problems. You don't want to do that on warning level issues. You really have to use that when the rest of the game is subsequently going to break. And the good thing is that you can either choose to continue your gameplay session, or you can use the retry button, and that will activate a breakpoint on the node that triggered the assert message, the pop-up. And you will be able to explore the whole call stack, see variable states, all those things, and it can be really useful to troubleshoot how to reproduce issue. Because when you have like a problem, like how to reproduce issue, you can tell your team this particular error message. If you get it, please scream in the open space, and the programmer will come over and see and investigate with you with what's going wrong. So this has been really helpful for us, in particular when wrapping up the project. A quick word of caution though. It can get really spammy, and people in your team can really hate you for interrupting the gameplay. So, please don't abuse it, and the game should run without any of those pop-ups. So, if one of them is showing up, it's top priority to fix. So now we will move into the shipping part of the game, because at this point, hopefully, we have created a lot of content. We fixed most of the gameplay issues. And as a small studio with no prior experience to actually, shipping a game without a ton of, super talented engineers around you, there are some topics that you can discover as you go. I chose 3 of them because, there are many more, but I think those we, kind of caught us off guard sometimes. The first one is build size tracking. Then we'll discuss initial chunk. We'll detail what this is. And the last would be save game versioning. So first, build size tracking. The important thing to remember is that, there are expectations about game sizes in general. The first one is most players are going to download your game. So you want the download to go fast, because it can create a little bit of friction and frustration for them if your game is gigantic. And there is also this great battle for storage space going on in almost, I think, every console player. And at some point in the lifespan of any console, installing a new game will mean uninstalling another one, and you want your game to create as minimal friction on this. And there are also some expectations related to the content of your game and the studio structure as well. Based on the playtime and whether you are AAA, AA, or indie, people will have different ideas of how big your game should be. And the last one, there are some actual physical release constraints when you are shipping on disk, and I will tell you a quick horror story about that a bit later. But what we did to keep build size in check was basically to monitor that during the whole production. We used TeamCity as a CI/CD pipeline. We created a small PowerShell script that runs at the end of the packaging phase, and what we measure is cooked asset size. So it is really representative of, in particular with a project with lots of blueprints, it's really representative of how big your game is going to be and how you can act on it. So we have trends, but we also, of course, have individual data points at the source of that. So this is the actual build size evolution of Expedition 33. So we started monitoring that in 2023. Up to a few weeks before today. You can see that there are a lot of variations that correspond to when we started caring about build size mid project. And you can also notice some data points in particular that stand out, like this one, for example. So having a tool like that is really useful to understand what's going on. And look into it. You have change list numbers, so it's based, of course, on nightly builds. So you might have a bunch of change lists from the day before to investigate, to know which one exactly is faulty, and then you can quickly figure out what's wrong. So in that case, it was like an unexpected bump in build size because we were trying different things on audio compression, and turns out, that was not the right audio compression to use, so we reverted that. It's also important to track the compressed game size because, of course, this is what you are shipping. And you will not always have a one-to-one mapping between your compressed and uncompressed size because some assets do compress really well. And for example, what you see here in the square is a phase where we were doing a lot of cleanup in some level sequences that had a lot of keyframes, like on every frame with the same values. So it's data that compresses really well. And when you remove that, well, it doesn't really change the compressed size for your players. So it's important to understand how your data is structured to not lose face in a cleaning up process. But you can see that by the end of the project, we were focusing more aggressively on that, and there were something closer to a one-to-one ratio between compressed and uncompressed. Also, not all platforms are the same, of course. So it's important to monitor values on all of your platforms to make sure, you keep your size in check. It's also important to raise awareness within your team about this topic. So what we did is create a Discord bot that would, on every build, notify everybody, which is useful already. But the key metrics we provide here are the cooked and uncooked size. So it allows non-engineers, people that don't go into TeamCity, to yet have a sense of how the build size is evolving. And you can even get producers to be aware of the build size evolution. And we do use Discord in a professionally, which is a good or not good idea, but we do that. We also do a full disk size report on the cooked asset list. This is exported as a web page. It is all interactive, so you can really dive deep into the hierarchy of files. And we share this link to basically everybody in the team, so people on their own can just go and check if their specific field or department is using too much disk size. So it also goes a long way in giving people in your team some autonomy in resolving issues. Speaking of which, It is a story time. So what you see here is an old scripture, long forgotten, containing ancient knowledge about platform disk sizes. Very epic, right? Platform A has 25 and 50 gigabyte disk size, and platform B has 66 and 100 gigabyte disk sizes. So the ideal size would be 50 gigabytes overall. So this is a message from 2023. Many years later, many years after this parchment was written, on a nice cold morning, a messenger came knocking on my door. Can I have an urgent IS ticket on Tom, please? Platform A build is over 50 gigabyte. That was a big problem. He was bringing the most unfortunate news. The ancient knowledge had been forgotten. Platform A had been forgotten, which was a big problem. But I swiftly assembled a team of the bravest warriors of the Falling Sand Guild, and within a few working days, thanks to their expertise, peace was retrieved across the realm. The end. The story is very short, but it's good that it's really short, because that was a major problem. We were a few weeks away from delivering a master build, and well, if you're past the hard disk size limit, well, you just can't. And in the end, giving ownership to the whole team about, and awareness to the whole team about build sizes allowed us to ship the game at 44 gigabytes, which is, I think, it makes sense regarding the amount of content and the playtime of the game. So now, creating an initial chunk. What do you mean an initial chunk? So can I get a quick show of hands that people that are aware of initial chunking, PlayGo, StreamingInstall? Okay, so it's a bit early in the morning to offer you a beer, but yeah, I feel you, I see you, and I feel you. Yeah, this topic can be a nightmare. So what it is, basically, the initial chunk of your game is a subset of the game data that players can download first and get into your game right away. Meanwhile, the rest of the game is downloading in the background. And when you are shipping a game, if you are over 20 gigabytes on several platforms, you do have to implement this technology. So what do we have here in our initial chunk for Expedition 33? We have gameplay systems, of course. So as I said before, it's a lot of blueprints. We also have two levels, the main menu and the bootstrap. And then we have actual content. We have the whole introduction in Lumiere, which is a large level with a lot of assets, a lot of cinematics. You have quests in there, you have dynamic level design. And we also have the Spring Meadow levels, which is, yeah, after the introduction, you actually get into gameplay, you have more enemies, tutorials, even more cinematics. So all of that is 3 hours of playtime and 15 gigabytes of initial chunk data. So I'm just gonna go for water real quick. So what are our chunks? Well, we do have the chunk 0, which is the default one in Unreal, and by default, everything will go in there. So yeah, this is the trash can chunk, so to speak. We also created chunks numbered in the hundreds to split our content, and we did that way before having to consider initial chunking, because we use Steam to distribute our nightly builds to people within the studio, so everybody can have the game up to date on their machine. And chunking data like that allows us to reduce the amount of writes that you have to do on your disk when you are updating the game. Because even though Steam is really good at delta patching, detecting changes in large binary files, when you are applying that patch to your file system, well, if there is an offset in data, you have to rewrite a lot of stuff. So we did that to make our own life easier developing and just updating the game locally without exploding our hard drives. And the chunk 999, which is special chunk that we created to hold all the initial chunk data. It has the highest priority, so if anything is assigned to chunk 999, it will go in there. What you ship as initial chunk is usually chunk 0 and an extra chunk, so in our case, chunk 999. So the question now is, how do you choose which asset go in the initial chunk? What you need, of course, is robustness, because if you are missing an asset from your initial chunk, you will have a broken game. And it can range from cosmetic, like missing texture, for example, or you can have like missing animation, the character is T-posing, this is not great. Or you can even have a full-on soft lock, because you are trying to load a resource, like, I don't know, an enemy for a battle, for example, but that resource doesn't exist on your hard drive at all. So it can really break your game. And we also needed flexibility, because we were still iterating on the game pretty close to release, because you are polishing the game and doing some bug fixes. So it was important for us to have a process that is as least manual as possible, to also support shipping updates post-launch without having to do too much work to keep the initial chunk up to date. So our initial approach was to think that things would work out of the box, right? Right? No, it didn't. Yeah, let me explain a little bit why. So all the assets that I previously mentioned, the core gameplay systems and the two content level that we have in our initial chunk, you can actually use recursive dependency gathering pretty easily in Unreal. All you have to do is create a primary asset level. So you give it your chunk ID, so 999 in our case, and you can apply that label recursively to all the dependencies that are associated with that label. So just from a few assets, you can, in theory, explore a lot of things, and then boom, you're done. Well, where are we? Introducing the technical depth of the project structure. What was going wrong for us doing this method? Well, first, we needed to do more reference cleanup than we already had done when trying to reduce build size and also doing some memory optimization, which I didn't go into much depth here. But yeah, we needed to do more cleanup, because any soft reference would end up in your initial chunk, and if you are past the 20 gigabyte mark, then yeah, you're cooked. But the bigger problem was that we were using data tables as registries. So, for example, you have a data table containing all the enemies of the game, and an enemy definition. You do have some display information, which is pretty lightweight, but you also have an outgoing reference to its actor class that you have to spawn during battle. And if you open up the reference viewer on our enemy data table and show like all the actor blueprints references, soft references going out, this is what you see. It is not great. We have around 400 outgoing references to basically all the enemies of the game. So if we were to explore recursively the dependencies from this data table, we will pull too much content to be within our 20 gigabyte limit. And also about levels, we couldn't reference levels directly, because in one of them there is some late game content. So if you pull all the references there as well, it will grab a lot of unnecessary content. So I put a spoiler shield to prevent people that haven't played the game yet from being spoiled. I will quickly lift the spoiler shield. So if you want to turn your head away or close your eyes just for a second, so I will lift it in 3, 2, 1. It is that level. So spoiler shield is back. You can keep your eyes on the presentation again. So we will dive into how we approach these two problems: the registry, data tables, and the late game content in levels. So new constraints that were pretty hard to deal with. We couldn't import entire levels, and we couldn't use a native dependency gathering in Unreal for the gameplay systems and content. We had to build asset lists manually. So the way we did that was by creating a few tools. We created a dedicated asset label, and we have, as you can see below, an explicit asset list, which we manually fill. For levels, what we used is the file openLog parameter, it's a native parameter from Unreal, which is available on your game executable, and it will, as you have your QA, doing runs of the game with that, it will generate a game open order.log file. Usually this file is used to order your pack files. It's coming more from the HDD era where it was important to have data that was like close together in your game being close together on the disk as well. But we are using that to build a list of assets that are loaded. So we have QA doing runs of the beginning of the game from the main menu up until the end of the Spring Meadow level. And we then import this text file into Unreal, into our primary asset level to populate the list. So yeah, on this view, I will add the different parts of our final process. So here goes this run with the file open order parameter and the path result that goes into the asset list. But we still might be missing some assets yet because not all the runs are exactly the same. We didn't have any automated process to generate those asset lists. So we will see a bit later how we worked around that. So now for gameplay content, we created a custom tool that is basically designed to explore our gameplay content, explore the data table that were causing issues, because we know how our game data is structured. So the idea is that you have different entry points, so like items, character, encounters. And from there, we explore all the dependencies. So the entry points are set up by game designers because they are the people who know your content the most. And we do a manual exploration of the rows. So for example, you have encounters that can reference enemies and that can reference items. So we find all the primary assets that are tied to each of those entries, and we also put them into the primary asset label. So yeah, for example, you have here the encounters referencing enemies. So from that, you get actor blueprints references. And the enemies also have a specific loot table on them, which is reference to our items data table. And items are defined by data assets and also textures that are used in UI. So this goes on the map. We have the gameplay data gatherer, but it's important to remember that it is only entry points assets. So for example, if you have an enemy blueprint, it will only be the enemy blueprint, and you won't have the mesh or the materials or the textures with that. So it's also incomplete. The way we approach completing this data set is by creating a dependency scraper that our engine programmer made. So the idea is that from a starting point, like a list of assets, you can explore dependencies, but by applying with respecting certain filters. So in our case, we were not exploring data table, composite data tables, and of course levels words that can sometimes be referenced in some sequences in particular. We do have a few more options, but being able to explore recursively with those filters applied was the key thing for us to keep the dependency lists in check. So this is a custom tool that runs from the editor. You can just pick a primary asset list, right-click, and it will run the tool and put the outputs in another primary asset label. So we apply that to the data we previously gathered with level exploration and the gameplay data exploration. And that's how we populated our 999 chunk. In the end, we have 27K assets in there. So it wouldn't have been possible to build that list manually, definitely. And even though we put ourselves in a corner with the data structure of the game, we try to find workarounds around that. And the last part of the talk is about save game versioning, because if you want to make changes after your game has launched, it's important to support that. because save files are crucial. Like, it's all the investment and the love people give to your game. It is stored in that very save file. So yeah, as SK would say, a most precious rock to be treasured. So creating a save file in Unreal is pretty easy. You have all your gameplay systems. You dump all this data into a save game object, and then it is written as a file. Loading a save file is equally easy. You take the file, deserialize it, sorry, into your save game object, and then your gameplay systems can read from that class to populate the runtime state. But then, yeah, changes happen, and you've changed the data that was contained in the save game class, and you can't load your old save file anymore, and SK is really sad about that. So how did we approach that? So we added a version number to our save files, defining different types for each version of our save files that we ship. So that way, when you're loading a save file, you do have a version number to refer to, and you can load it into the appropriate class. And then we define version upgrade logic to migrate older save formats into the new ones. And your gameplay system is always reading the latest version. And if you happen to be reading, of course, the latest version of a save file, it's already like, yeah, you don't have to do any migration. So it can go on like a chain, basically, that you can increase in length as you do changes to your game. But the problem we encountered at some point was that we were creating different types, a new type every time for our save game object that was accessed by the gameplay system. And having to change that every time was quite cumbersome. So what we did was create a proxy class, which is save game current, which is supposed to be always up to date. And that way, in your gameplay system, you are always using the same type. So save game v3 and save game current are different types. So what we had to do to migrate the data from a specific version to the current version was basically a property deep copy, because you can't assign one to the other with a typed equal. So when we want to add a new version of the same save game file, what we do is we do our change in the current version. So for example, here we are adding a Boolean, which is new data, and we duplicate that. I know. We duplicate that into a new numbered save game class, and then we write the version upgrade logic for that from the previous version. And then, as I said, we do a deep copy of the properties to have everything in sync. And this way, your gameplay system always have the latest data available. So this is the end of the talk. So a few takeaways before we go. What we learned from this production was to pick our battles. We adapted the scope of the game to the size and the skill set of the team. We played into our strengths. If I were to give any advice to like a starting studio, is to think a bit earlier than we did about shipping topics in general, build size, chunking, save files, memory optimization. It was also like a big topic for us on some platforms. And in the end, you also have to embrace the fact that you are gonna do crazy shit to ship your game, but that's also part of the fun of game development. So it's also okay to do crazy stuff. So yeah, thank you everybody, and you have the whole technical Sandfall team here at Unreal Fest. So yeah, come talk to us. They are in the front row over there, and see you on the floor. Thank you.